Okay, so good afternoon, everyone. So in this session, I will talk about uh, end-to-end deep learning solution on ARM architecture, from high-performance computers to microcontrollers. As you know, um, deep learning can be divided into two phases: training and inference. The model training with large data sets and advanced algorithms require very powerful computing capabilities. And HPC can provide a very good platform for this training part. As to the inference support, it is mainly done cloud side, but there is also a very good trend to enable it on edge devices, considering the privacy, latency, network availability, and etc. So from the latest top 500 rankings, we can see that HPC and AI are being converged. More than 50% of additional flops in the rankings were from NVIDIA Tesla GPUs. And half of top 10 and 122 of top 500 use NVIDIA GPUs. And we can see more and more AI, machine learning, deep learning workloads are being added to HPC applications with wide adoption of NVIDIA GPUs. Talking about the ARM architecture, I think we also have some good progress in this area, right? Just as Jill and Don mentioned, the Astra at the Sandia National Lab is the first ARM-based high-performance computers entering the top 500 list. Right. There is also some other ARM-based chip computers in the planning, right? So, for example, PostK from Japan, TN3 from China, and Catalyst UK, Isambed, and CA system. Sorry. The ARM scalable vector extension is also enabled by PostK together with interconnect and HBM2 memory, and will be used for some AI workloads. So it is very good. So besides the popular NVIDIA GPUs, there are some other accelerate options in the market. For example, MI60, MI50, Radeon Instinct GPUs from AMD. There are also some FPGA solutions from Xilinx and Intel, as well as some customized ASIC products like the Ascend 910 from Huawei. Okay, so the HPC support is also becoming a new service provided by major cloud vendors. Thanks to the powerful infrastructure for computing, networking, and storage. And the AI and machine learning services can be integrated with the HPC service seamlessly in the cloud side. Currently, the major CPU architectures used in the cloud side is x86 from Intel and AMD, and Power 9 from IBM. And we also, for ARM architecture, we also started a trip, right, for the Science Cloud provided by the HPC systems in Japan, right? So, and Amazon also just announced the EC2A1 instance based on AWS Graviton ARM processor. So, of course, there are still a lot of things we need to work together to improve this part, right? For example, for ARM, just as Don presented, there will be continuous improvement for the CPU architecture side, right? So, and we also need to enable the accelerators like GPUs, FPGAs, and ASICs on the ARM platforms, right? So we also needed to do some work to enable both the HPC and the AI software stack on ARM server platforms, including the frameworks, libraries, compilers, drivers. I think driver is also a very important piece because if you have no driver support for ARM architecture, you cannot do other software work in up levels. And specific for HPC, I think the multi-node distributed support and MPI will also be very important to scale out the workloads. Okay, so it is good to have multiple options, multiple hardware options for deep learning support. And the software fragmentation is also one critical issue we need to work together to improve in the ecosystem. There are multiple deep learning frameworks and inference engines from multiple vendors, right? So for application algorithm developers, it is difficult to switch between frameworks. For framework developers, they need to okay. So they need to maintain different backends for various accelerators. So for chip and IP vendors, they need to support multiple frameworks with some kind of duplicated efforts. And sometimes they need to provide out-of-tree support by forking the upstream. For ODMs, and the cloud vendors, they need to support multiple hardware and software combinations, right, to deliver machine learning services to their customers and users, so which is becoming more complicated. Okay, so the good thing is that the ecosystem, or maybe the industry, has quite clear understanding of the issues mentioned above. The open neural network exchange ecosystem was introduced by Facebook and Microsoft in September 2017. It is growing very quickly with more and more companies joining these ecosystems, including chip vendors, hyperscalers, ISVs, right? So the Onyx format is defined for framework interoperability. You can train a model in one framework, export it to Onyx format, and deploy it with another framework. Some Onyx tools also have been developed to convert existing models trained by various frameworks to the Onyx format. And the model zoo is maintained for sharing the models as a base for real deployments. So the Onyx interface for framework integration and Onyx Runtime are intended to provide hardware accelerations for inference support in some transparent and unified way. So the Onyx intermediate representation spec mainly has two parts. One part is neural network only, and the other is a machine learning extension. So the neural network only Onyx defines an extensible computation graph model, built-in operators, and standard data types, but it can only support tensors for input-output data type. And the classical machine learning extension can support data types of sequences and maps. Extend Onyx operator set with machine learning algorithms not based on neural networks. The latest version is 1.3, which introduced some important features like control flow, function support, enhanced shape inference, as well as some additional optimization paths. So the Onyx fee was also introduced in this release. There are some other features in the plan like quantization support. I think quantization is very important to do the inference on edge devices. And some test and compliance support, data pipeline support, and there is also some discussion specific for edge mobile IoT support in the ecosystem. Onyx is a standardized interface for a neural network inference on different accelerators. It provides a runtime discovery and selection of execution backends, as well as Onyx operators supported on each backend. The Onyx model format is supported, and you can do some online model conversion. The latest PyTorch 1.0, which merged and Cafe 2 together, already has a native Onyx support with the Facebook Glow deep learning compiler as the Onyx backend. The Onyx backend is a combination of software layer and hardware device used to run an Onyx graph. So the same software layer can expose multiple backends. And for the heterogeneous type of backend, you can distribute work across multiple devices internally. The Onyx runtime was open sourced last December by Microsoft, targeting a high performance and cross-platform inference engine for Onyx models. So the major advantage of this implementation is it fully implements the Onyx specification, including the machine learning extension. Multiple execution providers can be implemented in this runtime, like MKLDNN and ngraph from Intel, right? And CUDA and TensorRT from NVIDIA. And there will be more coming in the future, like there is plan to enable TVM in this runtime. There is some experimental support in this runtime already. So ARM platforms are also supported on both Linux and Windows, because Microsoft has some plan to use ARM processors on with their Windows operating system. So it is very good, right? So we can support more operating systems with ARM devices. Okay, then after talking about the challenges in the whole ecosystem, how we can collaborate in the ARM ecosystem. So the Linaro machine intelligence strategic initiative is to provide the best-in-class deep learning performance by leveraging neural network acceleration in IPs and SOCs from the ARM ecosystem through collaborative, seamless integration with the ecosystem of AI and machine learning software frameworks and libraries. The scope can be from high-performance computers to microcontrollers, right? So for HPC, data center, and cloud, there are some discussion about SVE-based optimizations for deep learning frameworks and libraries, as well as PCIe C6-based heterogeneous accelerator support. I think this including the drivers, compilers, and framework integration. For example, how we can support one customized ASIC in TensorFlow to do the deep learning training, right? I think the XLA from TensorFlow provide a good mechanism to do this. But how about other frameworks, right? There are some other frameworks in the market, right? MXNet from Amazon, right? CNTK from Microsoft, right? Paddle from Baidu. So how we can support all these kinds of frameworks with current situation, or maybe at the current status, the vendors have to support each framework separately, right? So because there is no one single abstraction layer or API for the vendors to support different frameworks. And just as I mentioned in previous slides, the scaled support for distributed training will also be very important to support the deep learning on HPC clusters. For edge node and devices, our initial focus will be inference support for Cortex-A SoCs. Although we can also do some training in edge side in the future, for example, on some edge servers. we need to have a common model description format and API to the runtime. I think Onyx is a very good candidate for this part. We also need to implement some common optimized runtime inference engine for ARM-based SoCs. The ARM neural network inference engine will be the base for this work. And we need to implement some plugin framework to support multiple third-party IPs, right? This can be NPUs, can be GPUs, DSPs, and even FPGAs. So we'll also cover the continuous integration testing and benchmarking and the related work to make sure that we can have a very good quality for this implementation. So talking about the microcontrollers, there are also some discussion about the CMC's neural network optimization on a real-time operating system, right? There are also some discussion about framework like microtensor and TensorFlow Lite. For this part, we needed to do some quantization improvements. We needed to do some footprint reduction. And IP-based accelerator support and optimization can be also very important in this area because, for example, you can add one AI IP, integrate one AI IP together with the Cortex-M processor, right, to have powerful inference capabilities. Even the CPU is not so powerful, but you can leverage the accelerator to do the work in the edge, even with a microcontroller. Okay, so the ARM neural network is an inference engine and SDK created by ARM. With the announcement in last September at Linaro Connect, it is now part of the Linaro Machine Intelligence Initiative for deep learning support. It provides a very good base for future collaborations. Up to date, the 100 main year efforts have led to 340,000 lines of code, and it is shipping in over 200 million Android devices based on estimation. So it provides very good confidence for us to use it as the base for future collaboration. So we can also see very good performance uplift in just 6 months with only software improvements. And we can get up to 9.2 improvements, multiplication. So yeah, I think it is very good. And we are also talking about with the chip vendors and IP vendors to have more accelerators supported in this framework. And we are also talking with cloud vendors like Google and Amazon for framework support. The alignment with the Onyx ecosystem can be very interesting, right? We are also talking with, we are also considering some potential collaborations with other inference engines in the market, right? So if you have any suggestions, please feel free to let us know. I think to have a better ecosystem for AI, we need everybody to work together and improve it. Okay, that's all for me. Thank you very much.
Thank you, Jamie. Any questions?